So what we did last lecture was define inner product spaces. So an inner product is a pairing which takes two vectors from a vector space and outputs a scalar. The scalar can be either a real or complex number. So throughout the entire business, we're working over an undetermined field of scalars. It's either R or C, though. It's not an arbitrary field. So given an inner product, we get a norm out of it by just taking the square root of the pairing of a vector with itself. So we proved that indeed that is a normed space. We defined a Hilbert space, so that's an inner product space whose associated normed space is complete. We proved the Cauchy-Schwarz inequality, which you can see there. We proved the parallelogram identity and Pythagoras' identity as well in any... well, this doesn't seem to involve the pairing at all. That seems to be a statement about normed spaces, but it's not true for all normed spaces. Actually, it's not so easy to see, but if a normed space satisfies that, then there is a pairing from which the norm arises. Okay, so in a way, this identity is true if and only if you're in an inner product space. This clearly involves both the pairing and the norm, as you see. So we also proved that given a vector u, so given a vector u in an inner product space, the pairing with u, well, in the second variable, because remember, the pairing is linear in the first variable and conjugate linear in the second. I'm going to start today's lecture by saying exactly what conjugate linear means, sort of more formally. That functional is a vector in the dual of v, and in the dual of v, it has a norm equal to the norm of u. So we also proved that. And finally, we ended the lecture by proving this relation, which says that, well, this was true this was true only in Hilbert spaces, right? This was the first time we genuinely used the completeness. And you can see why we would use completeness, because we're trying to construct something, and whenever you're trying to construct something, often there's a limit involved, so you need the limits to exist. And indeed, that's what happens. So given a closed, convex, non-empty subspace, well, no, subset. For our applications, it will actually be a subspace. And given a vector in H, then you can find a sort of closest vector in that subspace, closest in the precise sense that's given by that formula. Right, so that's where we ended last lecture. Okay, so the plan for today's lecture is A, to prove that every Hilbert space is self-dual, that is, it's isomorphic to its continuous linear dual. So that's the first thing. So that's an abstract statement about arbitrary Hilbert spaces. Well, as you might imagine, this is twisted a little bit because of conjugation, so I have to explain that. And secondly, I want to prove that L2 is actually a Hilbert space. Right, we don't know that yet. I mean, we know L2 is a Banach space, and we have some idea what the pairing should be. It should come from an integral, but we haven't checked that that is actually a Hilbert space. Once we've done that, then it will follow from the abstract theorem that L2 is self-dual, and that fulfills the promise made a couple of lectures ago. Okay, that's the plan for today. Then next lecture I want to talk about the Fourier transform, and then say a few words about what that means for our conceptions of space. All right. Okay, so I need to start by saying what this bar means. Okay, so let V be a complex vector space, that is a vector space over C. Then V bar is so it's another vector space over C. It's the same, remember what a vector space is, right? It's an abelian group together with an action of the field. So V bar is the same abelian group, but the action is modified. Okay, so given a scalar lambda, we make lambda act on a vector in V bar. So V bar is the same set as V, or the underlying set of vectors is the same. And a scalar acts on a vector V in V bar by the action in V of the conjugate of lambda. All right? So that's a vector space, as you can easily check. I mean, the point is this is a ring homomorphism, so that's what makes that easy to see why it should be true. This is called the conjugate vector space. Okay, so in the real case, I mean, I'm often working in a case where I don't know whether the field is R or C, and it's convenient not to have to spell it out. So if F is R and I write V bar, I just mean V. That's the convention. Okay, so in the real case, bar does nothing. Okay, it's also easy to see that if I have a normed space, and I change I don't change the abelian group structure, I don't change the norm, but I change the action of scalars. Well, think about the axioms for a normed space. The only place that scalars appear is inside an absolute value, right? So who cares if you took the conjugate or not? It doesn't even change the things you have to check. So that is tautologically also a normed space. There's almost nothing to check. Okay, so we call that the conjugate normed space then. All right. So that's convenient for the following reason. It means I never have to say the words conjugate linear again. Okay, so a function so let V and W be vector spaces over C. Well, okay, I got a bit ahead of myself. I need to say the words conjugate linear once to define what I mean. So a function is conjugate linear if, well, it's additive and it sends scalar multiplication by lambda to scalar multiplication by lambda bar. Okay, V and W, as I said, are both complex vector spaces. All right, well, I mean, the truth of the following propositions you can see just by reading this as lambda bullet FV. Right? If I switch to thinking about the bullet rather than just the invisible dot, then this would be f of lambda v is lambda bullet f of v. Right? So if I change my mind about the C linear structure on the right-hand side, this becomes a linear map. Okay, so there's a bijection between conjugate linear maps from V to W and linear maps from V to W bar. I mean, it's not a very exciting bijection, it's the identity. Right? I don't do anything to the function. I take a function, the same function between sets is conjugate linear if and only if it's linear, thinking of the lambda bullet action on the right-hand side, and if and only if it's conjugate linear, thinking about the base or the domain as having changed to the conjugate action. So, right, and as I said, to see why those are true, just read this as lambda bullet, and you could read that instead as f of lambda bullet v is f of lambda bar v. If f was conjugate linear, that would come out and be a lambda. Okay, so that shows this second claimed bijection. All right, so rather than say things are conjugate linear, I'll just stick bars on top of things and talk about linear maps. It's convenient because I've proved various theorems about linear maps, lifting, for instance, and I don't want to have to explicitly go through and state conjugate linear versions. That would be silly. Okay, any questions about the conjugate of a vector space? All right. Okay, so now we're on the way to proving 1 there. We know what the bar means. So why did I need that bar? well, let me just, this last point here, let me package it now together with the conjugate dual. So let this be an inner product space. Okay, so what's the point here? Well, the only observation here is the business with the bars, right? So, I mean, by what I just said, I could just as well have put the bar over there because the bar is just telling me this is conjugate linear, so there's really no difference. I might as well, I think in the notes I do it this side. Yeah. Right. So what's the point here? Okay. So I'm claiming, well, first of all, there's a function that takes a vector in V and gives me a continuous linear map from V to F. Well, that's that. We already know that's bounded and linear and therefore continuous and linear. So that's nothing new. I'm claiming it's norm preserving. Again, that's just what I said, right? Because the norm here, well, the norm space, which is the conjugate space, has the same norm. So, and I've already shown that the norm of the functional that I get is the same as the norm of U. So that's norm preserving. So really, the only observation here is the fact that I'm saying linear. And well, why is that? Well, it's clearly additive. That is, U plus U prime goes to the sum of the functionals blank comma U plus blank comma U prime. If I put a lambda here, that goes to a lambda there. That comes out as a conjugate lambda. So it's clear from the definition of the inner product that the map like this is conjugate linear, and therefore this map is linear. Okay. And similarly with the other guy, because this is actually conjugate linear, so it's really a map from V bar to F, right? Pairing with U in the first position is conjugate linear, so it's a linear transformation like that. It's bounded, so it lives in this vector space, etc. Okay, well, maybe I said this out loud last time, but norm preserving and linear means injective, right? Because if two things went to the same thing, well, the difference went to 0. Something going to 0 is precisely the same as having norm 0. Therefore, the thing you started with must have had norm 0 and therefore been 0. Okay, so this is also injective. That's true for any inner product space. I don't know if I've put this on the board before, but in an inner product space, two vectors are called orthogonal if their pairing is 0. That's symmetric, right? Because changing the order puts in a conjugate, but the conjugate of 0 is 0. So. All right, so what I want to do is change this lemma into a statement which is phrased in terms of orthogonality. Right? So as you recall from doing projections onto vector subspaces in vector calculus, the way you project a vector onto a subspace is you break it into a piece in the subspace and a piece orthogonal to the subspace. Right? So, I mean, we've talked about the piece which is in the subspace. That's the closest thing K. We might expect that is the difference, H minus K, might be orthogonal to the rest of K, if K happens to be a subspace. So we'll just prove that now. Okay, so let this be an inner product space. And well, I'm going to leave out the closed part because I'm not asserting existence of anything. Well, I won't in a minute. I'm exerting the equivalence of two conditions, which is why I don't need the closed. Right, then the following are equivalent. so first of all, that the difference, which way did I do it? V minus W, pairs with everything in W to give 0. Okay, so here you're thinking about there's V, there's a subspace W. It's not much of a subspace. There's W, and what I'm saying is, so maybe there's the origin, there's V. You should think of this as being my W, so that's V minus W. So this is what that condition is sort of saying, right? Saying V minus W is orthogonal to W, and that's equivalent to W being the closest point in W to V, in the sense of that formula there. That is, the distance, the norm distance between V and W is the infimum of all such distances as one of the components ranges over all vectors in W. Okay. Now, I'm not asserting the existence of such a closest point, just saying that, I mean, that's asserting that the second condition here is fulfilled by something. I'm not saying that. I'm saying that an equivalent condition to this is this. So I'm rephrasing it in terms of the pair. All right, so suppose we had this. Well, that puts us in a position to apply Pythagoras' law, right? Because we have orthogonality. So let's do that. So well, what are we trying to show? We're trying to show V minus W norm is greater than or equal to V minus Y, the norm of it, is greater than or equal to the norm of V minus W, right? That's the claim that we're making in 2. The W is the closest point. So let me just try and compute, well, the square for the usual reasons. And I'm going to do that by breaking it into sort of just something like the triangle inequality, right? Okay, but, well, V minus W is orthogonal to everything in W. W is in W, and Y is in W. I didn't say that. And, well, it's a subspace, so that's in W. And then by Pythagoras, if I've got two things which are orthogonal, I can compute the length of their sum by just doing this. All right, but that's greater than or equal to V minus W squared. So that proves 2. All right, so suppose 2 lots of Y's floating around here. All right, so we're supposing that W is the closest point, and I want to show that pairing is 0. All right. Well, why on earth is that true? Right, and that's in W. Yeah, right. So W is in W. I mean, I'm assuming it's the closest point in W. Apologize, that was a lowercase v. So that's in W. But W was the closest point, so that means this thing here, if I moved it over the left, has to have that inequality. All right, so this is a consequence immediately of 2. All right, so let's just rearrange that. Oh, sorry. Okay, so what we're going to do now is, remember we did this calculation last time where I took the norm squared of a sum, And these are arbitrary vectors. So that's just u plus v comma u plus v, right? When I expand that, I get u paired with u. Well, that's the norm of u squared. I get v paired with v. That's the norm of v squared. The cross terms, because of the conjugate linearity of the pairing, give rise to twice the real part of the pairing of u with v. Right? That calculation came up last time, and I just do it here. So this is equal to the norm of v minus w squared plus 2 times the real part of the pairing of this with this. Well, the norm of lambda y is this. Okay. All right. Well, that cancels with that. So we're left with 2 times the real part of lambda bar v minus wy plus lambda squared y squared. Well, what are we showing? We've shown 0 is less than or equal to that, right? So did I miss a minus sign? Yeah. Yeah, I'm sorry about that. I mean, you'll see when you expand this out. What? Oh, of course. But then that's a problem. Yeah, all right. Not that it matters, okay? I mean, lambda, I can change it by a sign, but I've done it this way in the notes, so I might as well be consistent, right? So that's a minus sign. That means this is a minus sign, so there's a minus sign there. All right, so then rearranging that, I get 2 times the real part of this is less than or equal to that. Okay, so I claim that's impossible. Well, this is for any lambda, right? And for any y. So what am I trying to show? I'm trying to show, I mean, w was fixed, right? W was the closest point. So v and w are fixed. I'm trying to show that v minus w is orthogonal to everything in w. So I want to show this is 0 in the end. So let's suppose for a contradiction that it's not. Okay, so suppose there's some y in w for which this is non-zero. Well, then I can set lambda to be what? Right, yeah. Okay, well, if that's not 0, then y can't have 0 norm, so this is a well-defined complex number. So I can take lambda to be this, and then this inequality, when I read it, says twice the real part of, well, lambda bar, which is v minus wy bar, times v minus wy, all divided by y squared, is less than or equal to this. Yeah, I did it the wrong way, didn't I? I mean, I don't want to prioritize this. I want to rewrite everything in terms of lambdas. That's what makes the contradiction apparent. Okay, so let's just fix that up. All right, so let me keep the lambda bar and rewrite this pairing as lambda times the norm of y squared. Well, that's clearly a problem. Right? Lambda bar is the modulus of lambda squared. So that is 2 times, well, that's real, right? That's the modulus of lambda squared. That's real times a real number. So I can get rid of the real part. That's lambda squared modulus of y squared. I'm claiming it's less than or equal to, I mean, twice of it is less than or equal to itself. And moreover, this is not 0. I mean, if either lambda or y was 0, this would be fine, right? But lambda is this, and that's not 0 because we assume the numerator was not 0 and y is not 0. So that's a contradiction. So what does that contradiction show? It shows that there is no such y in w with this pairing non-zero, which proves 1. So I'm done. So if you remember from linear algebra, there's a connection between orthogonal complements and duals, or quotients, right? That's sort of partly what we're talking about here. So we're talking about orthogonals, really. So let me make that formal here. So let V be an inner product space, and W a subset, not necessarily a subspace. Then W perp means all those V's in V such that V pairs with W to give 0 for all W's in W. Okay, so that's called the orthogonal complement of W. Complement for a reason you'll see in a second. Well, there's another way of writing that, right? Which is it's the intersection over all W's in W of the kernel of pairing with W. Right, so pairing with W is a linear map from V to the field. It's not just linear, it's continuous. So its kernel, which is the preimage of 0, which is a closed point, is not just a subset. The kernel is a closed subspace in the norm topology of V. So this is not only a subspace, a vector subspace, because it's a kernel of a linear map, it's also closed. So I'm taking the intersection of it, infinite potentially, it could be finite. Anyway, I'm taking the intersection over a collection of closed vector subspaces, and both vector subspaces and closed sets are closed under intersection. So this is actually, this orthogonal complement is both closed and a vector subspace. You'll notice me putting vector in front of the word subspace because it's become a little ambiguous what exactly a subspace is, right? It could mean a subspace of a topological space, it could mean subspace for normed space. I just mean closed under addition and scalar multiplication. Right, so the orthogonal complement, even of an arbitrary subset, is always a subspace, and moreover, it's closed. Okay. Well, suppose I started with something which was both closed and a vector subspace of V. V is an inner product space. Then, well, I said the orthogonal is something like the dual, so this looks kind of reasonable. So that means take the orthogonal and then take all the things orthogonal to the orthogonal. Okay. And secondly, V breaks as a vector space direct sum. Well, W and W perp are both subspaces, so I can ask, is every vector a unique sum of a vector in W and W perp? And that's what that symbol means, and that's true. And actually, this is the crux of the argument for why Hilbert space is a self-dual. So this is where actually all the activity is happening in that argument. All right. So let me prove the second claim first. All right, so what do I need to show that a vector space has a direct sum decomposition like that? I need to show the intersection is the 0 subspace.
So when you say closed subspace, you mean closed vector subspace?
Yeah, thanks. Yeah, I mean vector. That's right. So I mean a subset of the inner product space, which is closed in the associated topology, and which is also closed under addition. Which is also whatever. I think you're not upset by that. Closed under addition and scalar multiplication. Yeah. Okay, so to show this, we need to show both that the intersection is 0 and that every V in V can be written as V is, what letter do I want? Whatever, W plus Y, or W in W, and Y in W perp. Right, that's what this means. Well, I hope this looks reasonable, because suppose something was in W and in W perp. Let's call it V. So V is in W, and pairing V with anything in W is 0. well then pairing v with itself is 0, and therefore v is 0. Okay, so that's clear. Okay, what about this? Well, that's what this is for, right? That no, it's okay. Maybe I actually need Hilbert space here. Oh, well, let's see. So given v and v, yeah, I do. So right. So assume v is a Hilbert space. Well, what does that give me? So W is a closed subspace. So I can put it in for my K, right? It's closed, it's convex, any subspace is convex. It's non-empty. Well, if W is empty, well, it's not empty. I mean, it's a subspace. It's got 0 in it, so no problem. I mean, what I was about to explain was if W is 0, there's nothing to say, right? If W is 0, then everything is orthogonal to W, so this is just V equals V. So the case W equals 0 is also trivial. All right, so W falls under the hypotheses there, which means that there is a closest vector in W for every V in V. All right, so that's by whatever number that is. All right, the fact that that thing exists. Now we can use the characterization, which is given by this lemma, which is to say that V minus W is orthogonal to everything in W. But then, I mean, just think about this picture. We've written V is V minus W plus W. Around the other way, isn't it? W plus V minus W, where W is in W by construction, and V minus W is by what we just said in the orthogonal of W. All right, so that achieves that. Maybe I'll just leave this. So this is I mean, it's clear that W is contained in the orthogonal to the orthogonal of W, right? Because everything in W pairs with everything in W perp to give 0, so that's clear. To see that it's actually an inequality is just a little play with what we've done so far. So. Okay, so any Hilbert space decomposes given a closed subspace as a direct sum of those two pieces. Sorry? Well, I'm going to go back to my office and check, I guess, but standing here right now, I think I do, because who says there's a closest vector? Right? I mean, it's not for free. I mean, closest vector means a vector such that the distance from V, in this case, to that vector is the infimum of all such distances. Now, I constructed that as a limit last lecture. So unless I know it's Hilbert, I don't know that limit converges to anything. Yeah, I seemed to be more optimistic when I was writing the lecture notes, but I don't believe that guy right now. Any other questions? Anyway, our application is certainly to Hilbert spaces. So it's neither here nor there. Okay, so let's prove the theorem. This is given the name of the Reits representation theorem. There's actually several theorems that have this name. One of them I've mentioned already, which is a characterization of integrals against a measure in terms of continuous linear functionals on a space of functions. So that's also sometimes called Reits representation, and it's related to this statement. So there's a bit of a confusing point there in the literature, but in this context, Reits representation usually means the following statement. It's that, so let that be a Hilbert space. Then the map which we constructed before is a bijection and thus an isomorphism of normed spaces. Okay, so that's the promised statement 1 above. So this was U goes to pairing with U. Why did I phrase it that way? Well, we already know it's injective. That was for free for any inner product space. And I know it's norm preserving. So to show it's an isomorphism of normed spaces, I just need to show it's surjective, actually. Right. So, i.e., what's this statement saying? It's saying that given something on the right-hand side, that is, given a continuous, I could have just as well said bounded, given a continuous linear function out of a Hilbert space to the field, there is a unique representing element. Let's call it theta f. So what do I mean by a representing element? Well, I mean, we already know one way of getting continuous linear functionals out of H, which is pairing with something. And I'm claiming that's the only way to get continuous linear functionals out of H, so that if you give me any other one, there's something which has the property that the function f is just pairing with that thing. Right? That is to say that f of h is equal to h paired with theta f for every h in capital H. Right, so that's the representing that's in the name. Right, so that existence of representing elements is just another way of saying self-dual. Right? So this says a Hilbert space is self-dual up to this conjugate business. Okay. Here we go again. Well, I mean, how on earth are we supposed to produce an element of H from a functional? It's not so obvious, right? I mean, I have a, say f was C. So I have a complex number for every vector in H, and I'm supposed to somehow incorporate all of that information into a single vector. It's not so obvious how we're going to do that, but let's suppose we did it and then see what we're forced to do. Well, okay, so if that worked, then the kernel of f, which is all those v's in all those h's in H, such that f of h is 0. I mean, if we succeeded, that is, suppose we found a theta f which worked, then that would be true, right? So the kernel of f would be precisely all the things orthogonal to theta f, right? Because f of h being 0 is, maybe I should write that in. So that's all those h's in H, such that h theta f is 0. So that's the orthogonal to the singleton set with theta f in it. Okay, but here's the magic trick. Well, if I have W1 contained in W2, subsets, not necessarily subspaces, W2 perp is contained in W1 perp, right? Why? Well, to be in here is to say I'm orthogonal to everything in W2. If I'm orthogonal to everything in W2, well, I'm orthogonal to everything in W1, which means I'm over here. Okay, so that's clear. Okay, so let's just flip this. So theta f, well, that's orthogonal to the orthogonal of theta f, right? I mean, everything orthogonal to theta f is orthogonal to theta f, so that's what that inclusion says. But I had the inclusion, well, actually, that's an equality, isn't it? Yeah. But that's equal to the orthogonal to the kernel of f. All right, so that's where I've got to look for my theta f, right? I still haven't produced it, but I know where to look. I look in the orthogonal to the kernel of f, and I find some vector there. Well, so I don't know anything better to do, so let's just pick a non-zero thing in there and see what we get. Okay, so that's sort of a preface to the proof, right? Okay, so now for real, so choose a non-zero vector u in the orthogonal to f. I mean, there's no, at the moment, it sort of feels too optimistic to imagine that anything non-zero in the orthogonal is going to work. And, well, it won't, but we can tweak it. Well, first of all, why do I know there's anything non-zero in there? Okay, why did I say non-zero? Well, I mean, if f is the zero function, take theta f to be 0. That's unique because otherwise, if everything, then well, it's unique because if there were two things representing the 0 function, they would pair with themselves to give 0, so they'd be 0. Okay, so the case where f is the 0 function is fine. So let's just assume that f is not 0. Well, then the thing I choose to represent f, the theta f, well, that can't be 0 because if that was 0, then the left-hand side would be 0. Okay, so I know if f is non-zero, I'm looking for a non-zero theta f. So that's why I need to look for something non-zero, and by this I know it has to be in the orthogonal of the kernel. Well, how do I know there's anything non-zero in that orthogonal? By this. I mean, that wasn't for free. It's not trivial that the orthogonal is non-zero. Right? But the kernel of f, it's closed because f is continuous and the kernel is the preimage of 0. And it's a vector subspace for the usual reason. All right. So I know by this lemma that H breaks as the direct sum of these two pieces. It still doesn't quite argue for why I'm allowed to choose something non-zero here. Well, suppose this part was 0. That is, suppose it wasn't possible to choose such a u. Then I'd have this equality, but that says precisely that f is 0, and I've already handled that case. So I'm allowed to assume this is not the whole thing, which means this can't be 0. Okay, so it's legit to take a non-zero u in the orthogonal of the kernel. All right, so let's see how we did. Let's try and compute the right-hand side and see how close it is to working. All right, so one more detail. I mean, that's non-zero. So just dividing by the norm, or the length, rather, the absolute value of f of u, I can arrange for f of u to be equal to 1. Right? I mean, whatever, just replace u by this, by linearity. By linearity, that gets into 1, and it's still non-zero. Okay, so I might as well assume from the beginning that f of u is equal to 1. All right. So now I'm going to pair this thing with other vectors in H, see how close it is to being f of those vectors. Well, so what am I doing here? I mean, I expect that this is something like, well, so what does this condition tell me? This condition tells me this goes to 0 under f, right? Okay, so that's a decomposition. Sorry. That's a decomposition of K, an arbitrary vector, into a piece in the kernel and a piece which is, well, any multiple of U is in the orthogonal because the orthogonal is a subspace. All right, so that'll be useful when we make the following calculation. All right, so K paired with U is equal to, well, that decomposition, and half of it was going to disappear. And that part is in the kernel, and U is orthogonal to the kernel. So, yeah.
What is f of k?
Y is
So you said
here?
yeah.
Yeah. This is a number. So it's just linearity.
Cool.
Yeah. Yeah, so earlier f was taking values in a vector space or something, but for the moment it's just taking values in the numbers, so we know it's linear. Yeah. Any other questions? Okay. So when I break this up into two pieces, right, by linearity, well, that's in the kernel by what I just said, and U is the orthogonal to the kernel, so that's 0. So I'm just left with that part, and it's linear in the first variable, so the f of k comes out the front, so I'm left with this. Well, that's pretty close. Right? I've shown that for an arbitrary vector in H, pairing with U gives me the value of f on that vector, or times some annoying factor. But I just fix this by moving the U squared over. Right? Because this is a real number, just divide through. Okay, so that means that taking theta f to be U on the norm of U squared works. That is, it's a representing element. So that was sort of easier than you might have thought, right? We took the first thing that could possibly work, given this argument, namely a non-zero vector in the orthogonal, and we just had to mess around with its length, and it works. And it's unique, so it didn't matter which U we started with. Maybe I should say something about the uniqueness. Well, the uniqueness was covered by the fact this was an injective map, right? If two vectors, theta f and theta f prime, both represented f, that means they map to the same thing here, but injectivity means that that can't happen unless they're the same. Okay, so that's the representation theorem. All right, so corollary. Well, I guess I've stated it already. So if H is a Hilbert space, it's isomorphic to the conjugate of its continuous linear dual, which is the same thing as the dual of the conjugate, if you think about it. So that's true for any Hilbert space. Okay, so next lecture we'll prove that L2 satisfies the axioms. All right, so we'll leave it there for today.